a quick recap of what we did in the last class. So, what we said was if you have an RLC network and you are measuring, you are interested in finding the mean square noise at the output of the network, and this is a calculation that often comes about in practice. And if you want to do this, the straightforward approach would be to, as we discussed several times, every resistor R sub k is associated with a noise voltage source with a voltage spectral density 4 k T R sub k. We find the transfer functions from every noise source to the output, from which we can find the spectral density, and you can then integrate the spectral density all the way from 0 to infinity to obtain V0 the mean square noise at the output. Unfortunately, right, that is a very it is obviously a very laborious way of doing things, and it does not make sense to do simply because we are working so hard to basically get all these transfer functions and all these spectral densities, and finally we are throwing away, I would say, 99% of that information, because you are simply integrating that whole thing from 0 to infinity. So, yesterday we saw how one can exploit reciprocity, and the idea was the following. What you do is to inject an impulse current into the network and let E0 be the network, the energy stored in the network at t equal to 0 plus, right, and E infinity be the energy at t equal to infinity. All right, and we said that the mean square noise is nothing but 2 k T times E 0 minus E infinity by 1 coulomb square. I hope I got the spelling of coulomb right. All right, and we saw yesterday cases where E infinity was 0. We also saw cases where E infinity was what do you call non-zero, and this formula basically covers all the cases. Does it make sense? Okay. Now, let us kind of see this from another perspective, the same result from another perspective. So, when you inject a current into the network, right, what comment can you make about the Laplace transform of the voltage developed across these two terminals? Pardon? It is simply the impedance, correct. So, if you inject a current impulse, the voltage developed across the two terminals of the network has a Laplace transform, which is simply given by the driving point impedance of the network, correct. So, and what comment can we make about the initial energy stored in the network? How can we relate it to the initial voltage developed across the network? Or rather, okay, let me put it another way. What comment can we make about the voltage developed across the network at t equal to 0 plus? Let me call that VO. Pardon? No? Pardon? Yeah, use and tell me what it is. V of 0 plus is simply nothing but, I mean, what are all those theorems for? The voltage waveform is Z of S, correct, has a Laplace transform given by Z of S. So, what is the voltage at 0 plus? limit s tends to infinity s times z of s. All right. And so, what comment can we make about the initial energy delivered to the network? You pumped in a current impulse, correct? What comment can we make about the initial energy that's been delivered into the network? Pardon? Yeah, it's V0 plus times the charge. So, E0 therefore is nothing but the charge is unity. So, what is this? Or E0 by 1 coulomb is nothing but is V0 plus, which is limit s tends to infinity of s times z of s. Correct? All right. And what is E infinity by the same token? Well, E infinity is simply q times V infinity. And what is V infinity? Limit s tends to 0 s times z of s. All right. Okay. So, what is E0 minus E infinity? This is nothing but z of s. All right. So, what is this equivalent to? So, mean square noise is nothing but, oh I am sorry, actually we missed a factor of 2, right. Why? Remember that we have injected an impulse, right, and how much of, and what is the energy delivered by the impulse, what is the energy that is going into the network? The voltage across the network has gone from 0 to V0 plus, right, V0 or 0 plus. So, what comment can we make about the energy in the network? What is the energy inside the network? It is simply the integral of voltage times the voltage waveform times the current waveform that has gone into the network, and you can see that I mean there is of course a discontinuity, but if you interpret the impulse as being say for instance a thin pulse and the voltage waveform doing this, right, it is very clear that the energy that is going in, that is there inside the network is half q times V of 0 plus. So, this is 1/2 times this, and likewise this is 1/2 times s z of s as s tends to infinity. Okay. All right. So, the mean square noise is therefore, what is the mean square noise, people? Yes, it is simply k t times limit s tending to infinity of s times z of s minus limit s tending to 0 s times z of s. Okay. Okay. Now, it turns out that there is a simple way of interpreting this s times z of s as s tends to infinity. Remember, let us say you have a network, okay. and let us say you had the input impedance was some g of s. Now, if let us say this is R, this is L and this is C. Now, if I multiply this by k and by k, oh sorry, and what will the impedance be? It will be k times z of s. Does it make sense? Correct? All impedances have been scaled by the same factor, and therefore, the total impedance will also scale by the same factor k. Now, there is no necessity for that k to be real. It can be complex. So, for instance, if I make k equal to s, right. So, in other words, I multiply every impedance by the complex number s. What comment can we make about the looking in impedance? It will simply be s times z of s. Does it make sense, people? Right? Okay. Now, remember that this s is the multiplying factor for every inductor. So, what is in reality the impedance of this inductor now at a certain frequency s? Remember that the impedance of the inductor was SL, that is now been multiplied by an extra factor s. So, every resistor has now become S times R, the impedance of the inductor has become S square times L, and the impedance of the capacitor has become, what was the impedance of the capacitor earlier? It is 1 over SC, it is multiplied by this complex number S. So, this has become 1 over C, correct. Now, if we let S tend to infinity, right, how can you interpret this? As S tends to infinity, S times R becomes infinite. Similarly, S square times L also becomes infinite, and therefore, how would you interpret this limit of limit as S tends to infinity of S times Z of S? You open all resistors and inductors, right. Once you do that, you will get a network with only with capacitors, correct. Okay. So, yes, so therefore, how can you interpret S times Z of S? How can you interpret S times Z of S? Yeah, so basically it is the effective capacitance of what remains. Effective capacitance is just simply that capacitance, that number, correct, that S goes away because so let us say C1, R2, L3, okay, so this is Z of S, all right, and so the question is, what is S times Z of S as S tends to infinity? And one way of doing this would be to find the actual Z of S multiplied by S and let s tend to infinity, the easier thing to do is do it on a branch by branch basis as s tends to infinity and then look at the resulting network. So, what will this become? The capacitance will become 1 over C1, right. The resistance will become an open circuit, the inductor will become an open circuit, and what does this become? A resistance of value 1 over C4 equivalently, right. So, what is so therefore, what is Z of S times Z of S as S tends to infinity? Staring at this, what do you see? It is 1 by C4, and I mean in English it basically means that you open up all resistors and inductors, okay. You will get a network which only consists of capacitors. The equivalent capacitance that you see, right, is S times Z of S as S tends to infinity. All right. Pardon? Because the S times Z of S does not have dimensions of capacitance. I mean, S times Z of S has dimensions of capacitance, not it is not resistance, right? It's 1 by capacitance. Yeah, if the effective capacitance that you look, it's 1 by it's 1 by the effective capacitance that you look. All right. Okay. So, by the same token, therefore, how do you interpret limit s tends to 0 of S times Z of S? What should you do? Oh, well, that's straightforward. As S tends to 0, SR becomes a short circuit, S square L also becomes a short circuit. So, you basically say short all inductors and resistors, and you look at the 1 over, actually there should be 1 over effective capacitance. Looking. All right. Now, let us do this for our example we have chosen. What should you do for our network? What happens to C1? Yeah, it becomes a resistor value 1 over C1, right, and then what happens to R2? R2 becomes a short circuit, L3 becomes a short circuit, and C4 again as 1 over C. Okay. So, what comment can you make therefore as limit S tends to 0 of S times Z of S? What is the effective capacitance looking in? Effective capacitance looking in, it is infinite, right. So, basically because it is a dead short. So, therefore, the 1 over the capacitance looking in is 0, correct. So, what comment can we make about the mean square noise looking? So, what is the mean square noise? It is simply KT times 1 over C4 minus 0, which is KT over C4. Does it make sense? And is this consistent with our energy formulation? Well, when you, what is E0? You inject an impulse, where does all that current go? It sits on C4 because in the beginning all the inductors are open and what do you call the capacitances are shorts. So, E0 is nothing but 1 over 2 C4. E infinity, what happens? There is some initial voltage on the capacitor C4 as t tends to infinity. Well, the inductors become short circuits and there must be no current flowing through R2, that is what will happen at t equal to infinity, and therefore, at t equal to infinity, is very apparent that both C1, L3 and C4 are all discharged, right, or disfluxed, okay, and therefore E infinity is, what is E infinity? 0. So, mean square noise therefore is 1/2 kT 2 kT times 1 over 2 C4 minus 0, and this is basically kT over C4. All right. So, okay. So, this term basically has is often written as 1 over C infinity, where that 1 over C infinity is basically denoting, I mean this is now just a symbol, that is all. 1 over C infinity is simply, what is C infinity? Is the capacitance that you see when you open up all the inductors and resistors, and likewise this is nothing but, if you call this C 1 over C infinity, what will you call this? 1 over C0, right. So, this is written in, is also written in this form in the books. And this is what is called Bode's noise theorem. Come again. What you need to do is the following: you, to find C infinity, what you do is you open up all resistors and inductors. You will get a network with only capacitors. You find the effective capacitance looking in, right, using all your high school physics, right. If you have series, parallel, or some combination, you can do whatever you need to do, and that effective capacitance is C infinity. So, limit s tends to infinity s times z of s is 1 over that effective capacitance that you see at infinite frequency, right. And likewise, limit s tends to 0 of s times z of s is the effective capacitance you see at when all the resistors and inductors are shorted, and the total noise is simply nothing but kT times 1 over C infinity minus 1 over C0. Yes?
If the network contains only L and R like this, then
okay, I mean the question, I was hoping somebody asked this question. So, a very legitimate one. He says, oh well, what happens if you have a network like this? Correct. What comment can we make about the spectral density at the output at this node? How will this look like? At low frequency, this will be what will it be at low frequency? 0, because it is a high pass filter, right. At high frequency, what will happen? It will eventually tend to 4 kTr volt square per hertz. So, what is the total integrated noise of mean square value of so what comment can we make about is simply the integral of this noise spectral density, and what is this telling us? Oh well, this is evidently infinity, right, because that spectral density is constant and you keep integrating till infinite frequency, and therefore okay. So, this basically for this network, therefore for networks of this kind, right, you basically theoretically have this integral does not converge, correct, okay. And again this is telling us that, oh well, you know, if I simply put an inductor or resistor like that, I will get infinite mean square voltage, which basically means, okay, you know, evidently is something again which sounds too good to be true. So in reality you will never have a network like this, because, oh well, every node is associated with the parasitic capacitance, correct, and eventually the spectrum must fall off. Okay. And so in other words, this formula is only valid when the integral converges, right, which basically means in all practical networks this is valid. Okay. Likewise, you can show, it is straightforward to see that if you have networks with R, L and C, and you are interested in finding the mean square, if you short circuit the network and find the mean square noise current, you will be able to show, I mean, you will be able to write a similar relationship, right, involving L infinity and L 0 for the mean square current noise integrated across all frequencies. All right. So as I said, this is called Bode's noise theorem, and is a nifty little trick to know, to basically solve or to look at a complicated network and estimate what the, or determine exactly what the total integrated noise will be without going through any algebra, right, or complicated integrals. Okay. This is not the original proof of the theorem. The original proof of the theorem, you know, starts from Nyquist result, which is 4k, which you know to be SV of f is 4 kt times real part of z of s, real part j 2 pi f, correct, and we need to find the integral of, so what we need is basically integral S v of f df 0 to infinity, which is infinity, and this actually turns out that you can think of it as a contour integral in the z plane. This is the s plane, this is the sigma, and this is the j omega plane. So you take a contour like this and you integrate, you go along a contour like that in the z plane. What comment can we make about the poles and zeros of z? Let us say you have a passive impedance like this. What comment can we make about the poles of z? Poles are in the left half plane. What comment can we make about the zeros of the impedance? Where are the poles and zeros of a passive impedance located? They must be in the left half S plane. So if you go around, this contour therefore does not enclose any poles and zeros. So the contour integral around this entire contour must be, if you take z of s, which is a complex function, and the contour does not enclose any poles or zeros, right, the integral around the contour must be 0, right, and the it turns out that the radius, you choose the radius of this this contour as you know, r as r tends to infinity, correct. So it's I leave this as an exercise for you to work out, but this basically it can be broken up into three parts. One on that small circle whose radius tends to 0, and that is necessary to take care of potential pole at the origin, and this guy here, and it's a, I don't know if you are able to see this, but that contour integral is basically it will turn out to be one of those circles. The large circle will turn out to be limit of s times z of s as s tends to infinity, right, and the small contour will turn out, the small semicircular contour will turn out to be limit s times z of s as s tends to 0, and along the axis it will be it will turn out to be integral minus infinity to infinity real part of z of j 2 pi f, okay, and you can relate the two and get the answer, right. I mean, contour integration is of course a very valid way of finding the proof, right, but it's at least to me it seems a lot more intuitive to basically look at the energy going into the network and okay. It also turns out that the same energy based formulation, I mean approach also works when you as we will see later in this course when we have periodically operated switches inside the network, where the network no longer becomes is no longer time invariant, but becomes periodically time varying. Then you will find that this notion of using energy is more general, because energy does not depend on the concept of energy is independent of time invariant or time variant or linear or non-linear, right. Whereas when you say impedance, you already mean that the network is time invariant.